Hello, welcome to SOH again. Best office hours because you're part of it. 2024 Calculus AB question number 1. This question needs a numerical calculator to produce some of the results, even though you'll see that most of them can be done without it. But we will also practice with Desmos for this year. So the temperature of a coffee in a cup at time t minutes. So if there are units, be very careful with it. Not always in Calculus A, B, or BC you have units, but if there are, of course, this is something that we have to keep track of. Is modeled by a decreasing, so it's decreasing, is differentiable function CT measuring degrees Celsius. Now, between 0 and 12 minutes, selected values are given in the table shown. So we have a table here with a few values. Okay, great. Approximate the first derivative. So what we're going to do first is to go over the questions, get the main highlights, and in a minute or so we are done. And if you want to see the details, you can continue. Otherwise, you can solve it and come back with your 5 and go to the next one. Okay. So approximate C prime of 5. Well, what we will use is the kind of the slow formula, run over rise. And look that you have 3 and 7, and the value that they ask is 5, which is in between. So that's perfectly the case. Use a left Riemann sum. Well, this is like a lot of wording. Riemann was a great mathematician, was a disciple of Gauss, but the left Riemann sum means that we approximate the integral by the sum of different rectangles, and we take the value of the height of the rectangle. So when you have a function, you may have not perfect rectangles. It's like a trapezoid. So when it's left, you take the bottom one, the bottom height, instead of the tallest one. That will be the right sum. And the Simpson rule is kind of taking into account the trapezoid. In the limit of very small rectangles, you get the same results. But anyway, left Riemann sum, and we will do that here. We will do it by hand, not even with a calculator. You can use even Desmos to solve this. Now the next one, it says between 12 and 20 minutes, we can rate the change of temperature. So that's the rate of the change of the temperature, okay? So indeed, we have the change of the temperature, and then we have its rate. Okay, good. By this function, and C prime is measured in degrees Celsius per minute. Okay, great. That should be the case, right? Because we have C is degrees Celsius, and prime is a derivative, so like divided by the time, so by minutes. Find the temperature of the coffee at 20 minutes, right? Well, for that we will need to integrate, and in this case, yes. Even though this integral has this factor t here, then we will use a Desmos or a numerical calculator to do it, and then show the setup for your calculations. This is very important. You cannot just go and do it and show the number. You have to show the setup. So basically, you will have like the temperature of the coffee is the temperature of the coffee at your initial time, whatever it is. In this case, it's 12 minutes. Plus the integral from your initial time to your final time of your derivative function dt. And this usually is done with a calculator. Let's say Desmos, sure. Okay, oops. Okay, and then for the last one, it says that we have a very long expression here. Indeed, you could compute this derivative from the previous one, but determine whether the temperature of the coffee is changing at a decreasing rate or increasing rate. They don't tell us how much is the rate. That's why, in this case, if you find that this is positive, well, the rate is increasing, then this one is increasing, and if it's negative, then what happens is that the rate is decreasing. So you just need to check whether the sign is positive or negative. Of course, if you have a numerical calculator, you can substitute the values and get the number, and that's it. Okay, that was it. So if you want to continue to know more about how to solve each of these questions, stay. Otherwise, go solve it, and then let's go for the next one. So let's begin. For this, as we said, we are going to use a C prime of 5, so it's right in between, right 7 and 3. So it clearly is, the problem is being thought, to be exactly in the middle, right? And what you have to do then is to substitute the values that you see here, and just be careful not to mess up any of these things. And indeed, if you do those, you just get -4. Now, units are super important in this problem. There are units, so it's going to be degrees Celsius. If you want to use everything, degrees Celsius divided per minute. Okay, per minute. Of course, you could also say simply degrees Celsius per minute or something equivalent, and that's it. It is, notice that it's decreasing, so good. You know, it's decreasing, as they say here, it was decreasing. So that's a confirmation. Let's move on to the next one. So use the left, okay, let's do that. So for that, what we have to do here is, okay, so this integral here, which it will be exact, is going to be approximated. It's only an approximation by this sum of terms, which is basically is the length of the interval, so 3 minus 0, 7 minus 3, 12 minus 7. So it's going to be like 3, 4, and 5. So let's write it all. So 3 minus 0, multiply by the height, since this is the left one, then you choose this one, and then, you know, and then this one, and then this one, okay? So C is 0, so the first value, plus 7 minus 3, C 3, right? Plus 12 minus 7, C 7. Notice that our 7 is the beginning, is kind of the base, right? So we have here, okay? If it would be a right sum, it would be C3, C7, and C12. Okay, so if you just plug the values that you find here, this is 3 times 100, plus 4 times 85, right? Plus 5 times 69. And well, this is 300 plus 340 plus 345, 985. Of course, you can use a calculator, but you know, that's it. Now, does this have units? Yeah, but in principle, well, if you want to add units, that's the correct thing to do, but that's higher level than what you are required. When do you have to write units? When it's a quantity that you really know, it's very clear what it means. For instance, C prime is the rate of change, it's degrees Celsius per minute. In this case, what does this mean? This is degrees Celsius, right? It's an area, so it's going to be degrees Celsius multiplied by times minute. So indeed, this has degrees Celsius multiplied per minute, but it's nothing that is kind of intuitive. That's why they ask about the next one. What is the meaning of 1 over 12? Well, notice that 1 over 12 is the whole time elapsed, right? 12 minutes. So now that if you divide this by time, then you get back degrees Celsius. So the meaning of 1 over 12 of this quantity here is going to have the units of degrees. So it's a temperature. So we have integrated over 12 minutes and we divide by 12 minutes. So it's kind of the average temperature. That's exactly what it is. So it is the average temperature. And it's always good to add all the wording of coffee in a cup. Okay, yeah. Okay. And that's it. If you need to have the actual value, I mean, they say the meaning. That's not telling you to compute the value, but if you would need it, then this is simply 985 divided by 12 and degrees Celsius. Okay, and then, yeah, in this case, it's better to use a calculator and get how much it is. But you don't really need to compute it. Okay, it says interpret the meaning, not the value. Okay, so that's one more. Now, the next one, for this one, it says the temperature of the same thing, but says between 12 and 20, the rate of change of the temperature is modeled by this function. So that's the rate of temperature. And it says it's measured in Celsius per minute. Well, yes, because C prime of T is this thing, right? So the units are Celsius divided by time, minutes. So, okay, that makes sense. Find the temperature of the coffee at 20 minutes, right? So let's do that. So in general, you will have this question, you will encounter this question pretty often. So the final temperature of the coffee is going to be the initial temperature of the coffee and then the integral. So as I say, this you may find it many times. So it's kind of a standard procedure. And we have to substitute everything. So let's see. The final one is 20 minutes. Okay, cool. The initial one is 12. Yes. And then the integral is going to go from 12 to 20 of that expression that I'm not going to write. You don't need to write it. It's given there. Now, the only thing that we know is C12, because C12 is on the table. So it's 55. Okay, cool. So that's 55. But this one, you must find it through numerical integration. So how do we do that? Well, there are many calculators, but you know that you can use Desmos. So let's get and use Desmos. So what we have here is Desmos. Okay, great. So let's write our super function here. How do you do that? Well, first of all, you notice that it's in terms of t, not x. That's okay. You can just use t here. So let's begin. 55. We need the number 55 plus then the integral. You can go to functions. You can do it in two ways. You can go to functions, or if you prefer, you can just go in integral. And there it appears here, int. Then it goes from 12. Okay, let's go back to the numbers. 12. And then let's go here at the top and let's 20, right? And then the next deal is to write all these expressions. So minus 24.55 exponential. You can go here, click E, go back, click the power of what? 0.01. 0.01 t. Then you go here t. You could use also all with x, okay, but anyway you can use t. Then let's continue and divide it. So now we divide by t. Okay, we divide again by t. And then what's important, because the Desmos is not going to understand what we are doing unless we say here dt. But dt you can type it like this, like a word. And here you are. So you get the result that this is 40.329188. How many digits we need to, so it will be blah, blah, blah. You know, you can copy it again here if you want to make sure that, you know, everything's. So approximately, you can use like 3 digits, that's fine. So let's see, 40 after the period, okay? So 329 would be fine. And then that's the most important thing, I would say. You have to here record the units, okay? The units are super important. And that's the final temperature this time. Things that you can do with Desmos that are cool is, well, you could even plot this, just for fun, you know, this is additional, completely additional. But in order to plot this is just an integral, so it's not going to understand, you know, very much what's going on here. So then you need to use the letter x. So in this case, you know, you have to change this by an x. This is also by an x. Yeah. Let's do the following. Might be more interesting. Let's see how this changes. Instead of 20 minutes, if we would draw here an x, okay. Then it complains and it says probably there is no function here, right? Define. Okay. Well, let's see if we can see it. Oh, here it is. Yes. So you can see how this works. So we have this decreasing temperature, and at some point, indeed, let's say after 1 hour, approximately, right? Approximately 1 hour, you would have that the coffee goes to 0 degrees Celsius. So, well, that's unrealistic because, you know, it's going to get frozen, and then it's going to go even lower temperature, and indeed minus, you know, that the limit temperature is minus 273. So it's even going to be lower than, you know, the lowest temperature possible in physics. But, well, as they say in the problem, what you have, what we have here is that only for this range of times we can approximate the change of the temperature, or the rate of change of temperature by that function. So we cannot extrapolate that to the future, right? So much. Anyway, let's finish this. And this one, you don't really need Desmos, because what they say is whether the rate is increasing or decreasing. So basically, you have that C prime is C prime of t is increasing if its second derivative is positive, and C prime of t is decreasing. You know, so you have a function that is less and less if its derivative, but the derivative of the derivative is the second derivative, is negative. So indeed, it says, well, let's evaluate this for a time that is between 12 and 20. So what you can do is, okay, this number is positive, right? So, well, let's just say that this is positive. So this is a positive. Then e to the power of something is going to be, you know, this is positive 2. 100 minus 12 or 20 is going to be, you know, this is going to be positive 2. And then t squared is positive. So all this is positive. Therefore, what you have is that C prime is increasing. So you can say with more words that the temperature of the coffee is changing at an increasing rate, and that's it. Of course, you can always go to Desmos again, right? We can go to Desmos, and we want to see what happens with this function here. Okay, then this is a new function, so we can erase this one, and we just want to evaluate it. So let's write it just for practicing. Okay, it's not so 0.2455 multiply by e. So you go here just e, then you get the power 0.001 t, right? At the slider, that's what I wanted to show you. And then we'll go back here, down, parentheses, 100 minus t, and then divide it by t squared, right? So we go, you could do it all with x, but if you do it with x, you will get a plot, which is also fine. Now we add this slider, and we just want to have two, between 12 and 20, right? So you could say like 12, and then you see it's positive, and then 20, and you see it's positive, and it's clearly a decreasing function. It's purely decreasing function. So we don't expect a change of sign. This is not, it's not going to be 0 over t 12 to 20, right? Another way of looking at this would be that you come here and substitute all the t's by x. Okay, so let's see if we can do that. We can say x power of 2. Let's remove this 2, and then this one here also is x, and finally this one here is also going to be x. So in this case we're going to have a figure, and we can go here 0 to 12, right? 0 to 12, and you can see that from 12 to 20, 12 to 20, so we are here 12, right? And then 20, it's positive, so the same conclusion applies. So that's basically it, right? Now the thing that you can do just to finish is, if you want, that's additional because we are done, is to prove that that's actually the case, right? That we have that the derivative of this function is actually that one. So let me copy that, minus 24.55 e to the power of 0.01, right? Divided by t. Yep. But that's just additional, that's just for you because, we are the best. So we really want to be able to do this. This was C prime, so they could tell us to do all this. So it's cool. How does this work? Well, this is a constant. You have the derivative of the first one, multiply by this, right? And multiply by the denominator, minus, it will be positive, 24.55 e to the 0.01 t, and the derivative of this is 1. And then you have, right, divided by t squared, right? And then you can see how you can get the same expression as here, because there is this 100, right? So basically these two would be the 0.2455 that they like, and let's see whether they like the minus sign, okay, with t, which we have t here. So yes, you can see how this becomes just basically 0.24. There are many ways of writing the same thing, right? But you got 100 minus t divided by t squared. So it wasn't that hard, and this really is really nice. I mean, actually, they could have asked from the very beginning that we have this, get the units of this. So this we could derive the second derivative, and answer all these questions. Okay, and you should get to that level and get better than I. Okay, so see you in the next one. Looking forward to that. Bye.